Our speaker for today is Dr. Ramesh Raliya. Dr. Raliya is a pioneering figure in nanotechnology, has a rich academic background with a PhD in nanochemistry and a postdoctoral fellowship from Washington University in St. Louis. He is renowned for his patented innovations in nanourea and nano DAP, revolutionizing agricultural practices across 90 crops and 80 million acres. His work extends to biomedical applications, energy storage, and environmental solutions. He is the co founder of Smart Aerosol Technology and Chief Scientific Officer at Tidal Vision and serves as an associate editor for ACS Agriculture Science and Technology. With over 80 research articles, 20 patents, and 3 books, he has cemented his role as a global leader in nanotechnology and sustainable agriculture. Thank you, Dr. Alia, for joining us here today. The stage is all yours now.
Uh, Good morning, good afternoon, and good evening to people across the world from Washington State here in United States. So I'm going to walk you through a talk which is talking about bridging the gap between laboratory innovation and industrial implementation. What you see on your screen is basically a journey from 2008 to 2021. This is about an experiment or the work which I worked with many hardworking, dedicated colleagues and friends like you, those who are in audience and many who are not in the audience. I started with, you can see, a bench scale reactor on a laboratory bench, moved to the pilot scale to the industrial scale. Throughout this presentation, I will tell you various examples because I come from an agriculture background, both from the family perspective and an academic perspective. So I will take few specific examples related to agriculture, but I will try to correlate with different subjects so that you can correlate the things in your subject domain or what you do in your laboratory. I would like to start with one thing with this picture. I would like to ask a question to you guys. What do you see in this picture? If you just take a moment, you might have noticed a woman farmer who is my mother and another baby who is my daughter. But I would like to bring your attention to another picture, which is these black lines. What is these black lines? These are basically drip irrigation pipes. And these drip irrigation pipes, we used to have a big 3-inch pipe in our farm field in a remote village of India called Rajasthan state in Jodhpur. And the pipe was flowing all the time. We were growing cereal crops. And over the period of time, from my school to college and to the job now, we have seen that water is depleting. So the source is depleting. So what we went through that instead of cereals, now we are growing fruits. And we use this drip irrigation pipe, which basically putting drop by drop to this plant precisely so that you can grow the more crop per drop. So, but with this basic concept, I would like to show you that like how we made some research through the precision in agriculture and science. When I'm talking to you today, I am just the face, but I worked with many people and hardworking, intelligent, smart colleagues who gave me critical feedback, supported me in good and bad times, and navigated me to transfer this journey. I would like to appreciate all the individuals from these institutes whose logos are mentioned here, and even those logos are not here. I would like to appreciate everyone who supported me to navigate through this journey. During this presentation, I will take you through this pyramid, start with the exploration to development of the product, validation and optimization, scale and deliver and adopt. Why I developed this pyramid to take you through this talk The reason is oftentimes one thing frustrate me as a scientist when I was PhD student and postdoc, that whenever I used to go to conference or any talk, I used to see like a lot of papers which says that you use this application, you increase the yield by X percentage. You apply certain coatings, you improve the performance by certain percentage. So when I was seeing lot of solutions in these research papers, the one thing often frustrate me that why I don't see the solution at the same rate I see lot of innovations coming out. And that actually inspired me to find out those gaps, which actually bridge our lab scale work to the industrial scale. So what the industry want and what we are doing in our research laboratory, I tried to find those gaps and uh, did made some effort to bridge them. At the exploration stage, we often define our lot of objectives and metrics, what we are doing, what we want to achieve, and we establish certain measurable criteria to evaluate our research success. And that we often do through the literature review and certain benchmarking. Benchmarking means we compare our product or technology against the existing standards and competitors. And often we go through like a lot of research papers. I'm taking a particular example here. Even you see some of the papers here, like you can see the about the agriculture of 1921 and to the latest of 2024 of even last couple months. In my EndNote library, when I was searching, there was like more than 8,000 research papers and policy reports, which I I read and reviewed and put the notes in my notebook. But I found that if I summarize them all, agriculture problems can be summarized like this way, that they are surrounded by the topics, maybe like climate change, soil degradation related to water, crop nutrition and management, biodiversity, and economic pressure, technology adoption, regulatory sustainable practices, environmental impact, and food security. So these are some of the challenges when you summarize like over 8,000 paper in just one slide. You can say that these are the research gaps which people around the world are making their efforts to solve these challenges so that we can sustain the global food supply chain. And some unexpected events. These unexpected events can be like pandemics or war, and you can see some of these examples that how the fertilizer prices fluctuate based on these events. You can see from 2020 to 2023, and you can see during pandemic times how the fertilizer prices went up and so on. And the another reason is sometimes the resources are very limited to their particular geography. You can see from these resources that who manufactured, for example, these fertilizers the most. These fertilizers are manufactured only by few geographical geographical countries, which basically has the dominancy because of the availability of the natural resources and other resources required to manufacture them. And also the raw material required to manufacture these materials at the industrial scale. Why I'm talking about these things, I will tell you in little bit in next few slides. So to solve these agriculture challenges, there are like several different efforts are being made. For example, from precision agriculture to irrigation system, which I just showed during the introduction of the slides, and all the big technologies, whatever we are often read in our research papers introduction part, like robotics, artificial intelligence, machine learning, and so on. My group is particularly working related to nanotechnology. In nanoscience and technology, we deal with the material which is like 1 to 100 nanometer, at least at one dimension, and have the unique surface and physicochemical properties. And the literature says that the nanotechnology provides more efficient application of active ingredients. It improves the biological interactions and reduces the environmental losses. So it's people seems that it's more promising technology. And when you read the introduction part, what I'm particularly focusing here that what are the research gaps? Okay, I'm trying to highlight that what are the research gaps that why most of the promising technology remain as a research paper, remain as a thesis, remain as an excellent project report, but why that technology doesn't get translated from lab to land. So I'm trying to find the gaps here with you, that you see this is an introduction part, particularly related to when you see any paper related to agriculture application in nanotechnology. I'm just taking that as an example. In the introduction part, most folks was talking about unique property 1 to 1000, 1 to 100 nanometer, high surface area to volume size ratio, quantum effect, and environmental sensitivity. And then there are a lot of other things. What is in yellow highlight is most common, and then you see about 7 different type of properties written in the introduction part. But what the stakeholder sense when you talk to industry folks share that they miss this correlation as a part of our agriculture related experimental design and observation. When I talk to industry people, when I talk to investors, they say that, okay, you are talking about high surface area to volume size ratio, but let's go to your experimental section. Do you see that effect? Do you see the quantum effects correlation? And then I move to material method part of our research papers. In material method part, often we say that we outsource certain analytical reagent grade or ACS grade chemicals, or we purchase some nanoparticles. And then we say that we synthesize certain nanoparticles according to XYZ methods, and then we mention certain characterization techniques, and then we test this. And then we compare with certain controls and mode of action in our result and discussion part. But oftentimes, we see that when we translate our result and discussion section, we say that these nanoparticles, this effect which you are showing, that depends on multiple properties, like how nanoparticle structure and nanoparticle properties play the important role. Like, for example, size, shape, charge, crystal phase, stability, solvent type, method of synthesis. But when you see the research paper in a single research paper or a series of research paper by a particular research group, we don't often see these things comes out. And because of that, the industry's feeling is that they are not able to translate some of the result that we observed as an excellent observations in the lab. So they are not able to translate because they don't have the full information that how they can replicate the data which you generated in the lab. And that's why sometimes the industry feel lacking of that. The second question comes about the development. In the development, once we have a really good research product, we have to go to the next stage. And that is beyond the research publication or filing the patent or getting a particular uh, milestone in our academic journey. And in the development, this is talking about the proof of concept development, that you develop a proof of concept to demonstrate the feasibility. And these feasibility can be like multiple feasibility. It can be technical feasibility that you can scale up. It can be economic feasibility, that your product which you developed can be affordable by the people in many different economic background. And operational feasibility means that it can effectively get scaled up and take to the next level. I will take an example here, that what our group did in the lab, that we started working on these synthesizing nanoparticles. And we synthesize these nanoparticles through various different methods: physical, chemical, biological, plasma synthesis, aerosol synthesis, and so on. And why we explored multiple methods to synthesize these nanoparticles, to ensure the feasibility that we can retain the nanoparticle properties and we can scale up the process, and which process is more economically feasible, both for the industry and both for the end user. And also more particularly, that when you don't use the ACS or reagent or AR grade chemicals, because when you don't use AR grade chemicals at the industrial scale, how much you have to compromise on your product quality or product properties. And what other parameters you can take care so that you don't have to compromise with your product quality, but you can take your product to the next phase or next level. So what you see here, that we started with molecular state particles, we make the particles, and then you see like different shape and size of nanoparticles. When we see the scale up in the lab, but you see a couple of things here, that in the laboratory, we often see in the fume hood, those people from chemistry background or chemical engineering here, they might be able to recognize these kind of setups, that when we synthesize nanoparticle under aerosol reaction setup, then you see like a lot of carrier gases, precursor sources, and so on in the reactor. But when you go to the industrial scale up, you really have to tell systematically that what are the flow rate. You have to optimize your process. You have to optimize the reaction conditions. You have to simulate the scale up reaction process and provide a process flow diagram, and also the safety and risk assessment of the processes. And lot of other things which industry require, for example, material energy balance, how and what kind of equipment constructions, process refinement, operational automations, and so on. And these are very critical to get the technology from this kind of bench scale to the industrial scale setup. And once you have that product ready, then you have to optimize the performance under various settings. What you see on your slide is the delivery and tracking of nanoparticles on various plants. You see different type of plants here, and then different method of application. For example, the one of the product we developed is a fertilizer product, which can be applied through foliar applications, drop cast, aerosol method, soil application. And then you really drill down towards the mechanism of action, that how your material perform and why it is performed. Because the perform is important, but why it is performed, it is more important to communicate and to convince the customer and the various other stakeholders, that may be like regulatory agencies, that may be like policymakers, that may be your end user customers. The another important part, once you have developed this type of product or prototypes, the another important section comes is validation and optimization. What this validation and optimization does, that you validate the prototype which you developed as a working model, then you validate the testing at the functional usability and compatibility, and you optimize its performance from the cost perspective and from the quality perspective. And then you validate these things in the real world scenarios. And why you need to validate? Because you validate the things that as you scale up, you don't compromise with the quality of the product. And then your product perform in the same way that it performed in your lab. When you are making 1 milliliter product or 100 milliliter product to a thousands of liter or million metric tons of the product perform in the same way. And that actually provides you the feedback from your customers and various other stakeholders. And based on that feedback, you do the iterative improvements, and you bring out and refine the technologies. Here, for example, as an example, that when we develop a product, we test it in an hydroponic condition before coming to the field, and then we test it in the controlled field conditions. And in the hydroponic setups, you see the different growth parameters, and then you optimize the products on the multiple crops. You do the rate titrations, you do the different test parameters, comparison metrics, and life cycle assessments of your product. I'm taking here an example of agriculture, but these stage gates apply across the subjects, be it like a chemical process or biological process or a biochemistry or a microbiology or immunology or physics, like all kind of products, they go through certain stage gates. And these are some of the common stage gates that bridge the innovation from lab scale innovations to the market. And this is an example of how we tested the products in the field before bringing the products into the market or in the customer's hand. So now the question comes that you develop a product. For example, these are some of the pictures of 2018 When we develop a product, we hypothesize that this product works like this way, the best way. Lot of news press release related to your research papers, research articles, innovations. You got few awards and innovations, but what is the important things? It is important that someone who believes in your technology, someone believe in your skills and ability to take the product, take your discovery to the next step. And for that, one of the important things you require is the financial support. And the financial support and the mentorship, which basically guide you to develop the technology from lab to a prototype stage. And once you have a prototype stage, they can these funding support and mentorship connect you with certain folks or certain groups, which basically can help you to take the technology to the next level. And here I mentioned the work of this cross-pollination. Cross-pollination is a terminology in agriculture where pollens get cross-pollinated. Why I say here that when you develop the product, you interact with your lab group, you get the feedback from your professor, but it is very important that you talk to some people who actually not from your field. So you talk to them, get the feedback, and that will give you the two feedback. One, that can you communicate your technology to a non-technology, non-subject background person? That is, communication is a lot more important when you translate the technology from bench scale to industrial scale. And entrepreneurship, I'm happy to see that across the world, industries and the governments are supporting innovations through the various entrepreneurship centers, both in universities and also through the various startup pitches for the small scale companies or startups. And ACS, I can see that like various journals in the ACS publication also provide a lot of different awards and recognize great technologies, which actually help them to build the network and take to the next level. The picture you see in the corner which just appear here, it is just my first check. It doesn't matter that how big is that, but that inspire, even it is like just $100 check, that basically inspire you that what you can make in your lab, you can actually sell to the customer. Okay. And once you repetitively sell, repetitively increase the quantity and the demand continuously from the customer, that shows that how your product works. And once the technology developed, the question for me when I develop the technology that either wait and watch or take the first step. I took this recent example that when artificial intelligence, there is no clear policy that what to do for the artificial intelligence. One of the company launched their product and then other people followed them. So as a scientific fraternity, we are the forefront in the technologies. So sometimes we have to take the next steps rather than just waiting and watching to create someone comes and create the path. And that basically comes that scale and deliver. And in the when you scale and deliver, you have to identify where is your market opportunity, what is the market size, what is the product development stage, and various investment, human resource, and what other requirements which you require to roll and out. I'm just giving an example related to one of the nitrogen product that we rolled out from lab to land. What these picture shows that globally, when you talk about the fertilizer product, you talk about a lot of different type of a plant require about 17 different type of elements essentially, and some of the literature says 18 to 21 different type of elements as an essential nutrients or desired nutrients to grow the plants bigger and better. But if you see from 1961 to 2021, one of the biggest market is the nitrogen fertilizer across the world, and among the nitrogen you see is an urea. So what you see in this slide is a market size and market opportunity. But what you see here is a customer pain. And what is this customer pain is talking about the regulations and regulatory development across the fertilizer. You talk about Asia Pacific to European Union to the Latin America or North America, all the countries putting regulations related to these particular things. And when some regulations come, some policies are development, this shows that there are some growing concern about the existing product. So that shows that there is a opportunity to do the more research. And and for this particular problem of the nitrogen losses, to the atmosphere. That what you put on the ground in the farm field, 50% of that goes to the environment. To reduce that, there are like a lot of competitors who are coming and doing the research and helping the community to find out the solutions. People use microbes, people use electric sparks, inhibitors, various coatings, different type of sustainable practices to increase the efficacy of the product. Our group worked on this nanomaterial, nano biomaterial based technologies based on nanotechnology. And and one of the things that when you have the product, the question comes that in which market to enter. So you have to identify the right market to enter in order to have two things. Either you see the biggest business opportunity, or the second thing, you see the biggest impact. So largest impact, largest opportunity. I was uh, I was looking at globally when you look at the nitrogen and phosphorus. So the biggest nitrogen fertilizer being used in China, but most of them they manufacture by themselves. The second is in India, which basically consume the second most user for the nitrogen fertilizer, particularly the urea. And they produce some amount of nitrogen, but they import lot of fertilizers. And then the United States, you can see that over the period of time, how India and United States increase their fertilizer use, particularly to the nitrogen. So one night I was sitting in the lab and I was thinking that what to do, because it frustrates, right? Because you have the technology, you always write the research papers, you present in the conference, but how to help the people like my parents, right? So what I did that in the midnight, I was sitting in the lab, I drafted two letters or two head of the nations. One is in India and another in United States. The one guy uh, uh, found the opportunity to open the letter, and the government of India invited me to talk about the nanotechnology based nitrogen and phosphatic fertilizer back in 2017. And this is how my journey started uh, of the rapid translation. I came to India, and there was no guideline to translate the nanotechnology based product from lab to lab. So there was a guideline which was developed in 2018, and then eventually it was released in 2019 to evaluate that how to test these materials, because these are novel products. As a researcher, you know that when these products are safe, in what circumstances these products can be toxic. So you require a common guideline so that everyone can understand, everyone can on the same page that how these products are safe and sustainable to be utilized, and under what circumstances these products can be harmful. And this is the another thesis which I wrote in 2020, 2020 after my PhD. I never expected that I will write another thesis because I was enough with 2012 my PhD thesis. But I wrote this thesis which basically talks about the evaluation report of some of the products related to like nano zinc, copper, uh, and then nitrogen and phosphorus, and we submitted this to government of India. And I appreciate many officers and policymakers in the government who helped us. They asked me the tough questions, but also they helped us by asking those questions to explore our products and take to the next level. And I always say that one person cannot move the entire needle. So you really require to build the team. And it is very important that you build the team which is interdisciplinary team. You need the people from background of mechanical engineering to chemical engineering to chemistry to botany to biotechnology, instrumentation, electricians, administrators, policymakers. So you need all kind of combinations in your team as you translate from one phase to another phase. And that actually, why it is important, because these different background, academic background or knowledge background people, one thing is that they provide you the different feedback. So based on their feedback, you can improve either your process or you take to the next level. And you can see that most of the folks are having the mask on their face. So you can see that most of the work we were doing during the pandemic period. So that's why like we have the mask outside the lab. So when you translate the technology to the outside, when you are like in the frontier technology, when you are working on frontier technology, the question comes that how to translate. So for me, when I was translating this product of nanotechnology from lab to land, I I took some of the I took experience some of the experience from the other industries who translated my product or the lessons so that I can translate the technology. Uh, so what I did that I took the lesson from where the nanotechnology is most translated. So if I see the examples, the most examples are related to energy, sensors, circuits, biomedical engineering, or coatings and filters, where the nanotechnology is being applied. Why? These are most successful industries where nanotechnology is translated much better. When I compare to the agriculture input materials, I found that in these industries, the material require in the in the small quantity. The second thing, they require analytical grade raw materials to manufacture because you really don't care about the dollar, you care about the efficiency and efficacy. For, for example, when we go to the hospital, we do take care of the cost of the medicine, but the very first thing we ask to the doctor is that, doctor, please give me the medicine so that I can be cured immediately, right? You require, when you go to purchase the phone, you ask for the good battery life, you good cybersecurity, and good performance, rather than you ask that, hey, take the less money and give me the compromise on certain qualities, right? So why this nanotechnology success on these? Because of they require in very small quantity and good amount of materials, which we often use in laboratory, so you can easily replicate at the industrial scale and take to the next level. And they have, and one thing is, like I mentioned at the bottom, that often in these technologies they are manufacturing used product, or they are end use product. So if you see most of the things, they are manufacturing used product. For example, the chip, the mobile you carry, which has a memory card, and that memory card is basically having a chip, and chip might have like certain nanoparticles on the top of that, and you don't buy the chip, you buy the phone, right? So this is manufacturing used product versus the end use product in agriculture, where you develop the product which is being actually used as a nanoparticle by the farmer. So you require a more detailed label, more detailed studies, and then enough warning labels or harmonized standards. So enough warning labels means they have the labels that, hey, don't put your electric circuit near the heat, right? And that's more than enough. Whereas in agriculture, you have to detail layout because you develop the end use product to the next level. I took this lesson, and then I what we did that we designed the industry, which is not like the one you see on the one side, but on the other side, a kind of an concepts we took from these industries, which translated successfully this sophisticated technology from lab to lab. What the picture you see here, these are the multiple pictures from one of the industry where I was involved and translated. The top one is the field where this is the field I got when from the industry partner, and this is how we started. And you can see the first board we put as a man plant building, and then this is how we built these sophisticated plants. And India now have like 4 nanomaterial manufacturing plants up and running, and there are several coming and in development. And various stakeholders are getting involved. What the pictures you see is basically brings about the title bag to bottle, right? I mean, what the pictures you see, often you see these kind of pictures when either the iPhone launch, or maybe sometimes on the Starbucks coffee you see the long line, right? But this is a picture of one of the remotest field in the village where people are in the lineup in the queue to purchase the fertilizers, and this folk having a fertilizer bottle in his hand. This actually gives me a satisfaction that people, millions of people like my parents, who can have the product today in their hand, which once upon a time I was dreaming in the lab and thinking about writing paper and presenting the poster, filing the patent, and then translating to the next level. But the important question comes the next is the adoption. And when you adopt the product, when you translate the product, it gives you require a lot of context and feedback. You require to educate people in a very simple language. The why this is more important, because you remember, or you might have remembered, that when we first time got the cell phone which was having like touch screen, even the touch screen phone was in the market, we often go to the shop and we buy the phone which having the certain buttons, right? Because we thought that, oh, touch screen will get spoiled in few days, few weeks, and don't know where to repair. So let's buy the things which we can easily like handle and operate and we are used to. So sometimes we have to educate our customers in a very simple language, that how to translate the product, and how to utilize the product. And other thing, you talk about the impact, right? What here, this is a small contribution I did to the farming community and millions of the people like parents. I provided this technology at free of cost to the government of India, so that it can be translated and can provided to the millions of people like my parents. And some people, this news headline says it's free, but I consider this as an investment to the environment and to the future generations. Uh, and here you,
आगे बहुत सफलता दिखती है। आदरणीय सभापति जी, हम नैनो टेक्नोलॉजी को एग्रीकल्चर में लाने में प्रयोग अब तक सफल हुए हैं। हमने नैनो यूरिया में बहुत बड़ी सफलता पाई है, नैनो डीएपी की दिशा में सफलता पाई है, और आज एक बोरी भर खातर लेकर के घूमने वाला किसान एक बोतल के खातर से काम चलाएगा।
So what the Prime Minister here was briefing to the Parliament in recently in 2024 about this technology, right? And this news articles and many news articles like this, they are talking that one of the product which I translated in India can save $40 billion by 2030. And I remember that when I started one of my first journey, I was just having $400 in my pocket. And today, when it says the 40 billion, sometimes I just think about the how many zeros in that billion. So it's not about the money, it's about the impact. And impact, about the impact, the economic impact for the policymakers or for the country, but also the impact to the government and to the environment and the sustainability. Recently, I was reading a report which was released by International Fertilizer Association, which is talking about that nano urea is an example of an emerging technology that has potential to enhance crop yield and reduce the nutrient losses through the nanotechnology, with some commercial success in India today. So what these things are telling me, that like this gives that how a small lab scale experiment can have larger impact. And then we all often talk, there are like another product coming into the market, is called nano DAP. And when you see these kind of economic impacts, and sometimes when the manufacturing company launch and the share market jumps by 7%, I mean, whether you invest or not, but these things makes happy, that like, oh, what you did sometimes in your lab, you are like doing experiments in the midnight and writing letters to here and there. And today, if your product technology can fluctuate certain things, influence certain things, that gives the satisfaction and take the things to the next level. And beyond that, I would like to like highlight these are like some of the key things, that since 2019 in India, through the technology which one of the technology which my lab group has translated, has created more than 20,000 jobs. We have created more than 1,000 highly skilled jobs, which are like sophisticated folks who just run the plant, design the things, research, developments like that. And the nation registered on the GM, genetically modified crops, adopted the nanotechnology, and today it is at the very large scale. We have tested this product in more than 20 different countries, more than 90 different crops, already being applied on 80 million plus acres, and had an investment of over $300 million, and it has potential to reduce the carbon footprint. And we have also increased the capacity development of more than 100 million in terms of equipment and infrastructure. So these are like some of the impacts which I highlighted here just to show that how a single experiment, which once you dream, can create a massive impact uh, at the society level. But all is not blue always, and all is not green. There are like a lot of challenges as you walk through this pathway. And these in this journey, there are certain challenges because when you deal with industry, as being an academician, being a researcher or research scholar, and also because I'm from the farmer family, so I'm also the customer of the product which I created or I translated, right? So I have to think about my product both from the business side, from the creator side, but also from the market side, because what you create, the product which I made is being purchased by my family members. So I don't want to send or ship anything which doesn't work, anything which I cannot recommend to my dad, anything which I cannot recommend to my friends or family members. So, but the industry has the best versus first policy, like whether to make the best product or just be the first. Then the scale and quality. Then there are certain conflicts in during the journey. Many people have their personal and professional conflicts. There are a lot of cross checks which we do generally in the lab, but sometimes we lack these things in the industry. And sometimes the copy paste, for example, the one product launch, and then you see like several different people and products, such products comes into the market with just the product as like nano, and then how you can control those quality and how you can convince the people. And then there are like certain groups which might target you personally and professionally as well. There are like certain IP rules, advisors, human resources skills. These are some of the things which you really feel both as a technical challenge and both, and the another side is non-technical challenges. So we have to deal with these. These are not the barrier, I would say. These are the things which we can easily tackle and can understand, get the feedback, and take to the next steps. These are not the barrier, but these are just the stimulator, and these are just stressor which can further motivates you to take that technology to the next steps. So I hope that I was able to take you through this journey of exploration to development, validation, scale, deliver, and adoption. Because of time constant, I was walking you through this pyramid very fast, but you can find me over the email or on the websites. You can communicate me through various different platforms, and you can contact me if you have any more detailed question. Of course, you have the chance and opportunity here to ask, but if you have more question or later, anytime you can reach out to me. With that, I would like to mention to the academician or the researchers around the world, I invite you guys to submit your frontier research related to nanotechnology in sustainable food and agriculture to this special edition, which myself and some of the highly excellent editors are editing these three journals: Journal of Agriculture and Food Chemistry, Agriculture Science and Technology, and Food Science and Technology. So I invite all the researchers around the globe to submit your research paper and review papers and perspective in this special issue that we are having. With that, I would like to thank you to everyone, to all of you who joined me today in this talk and in this conversation.